Max Briel. We will go first, and then Petra Tang. So, Max, if you'd like to start off, welcome along.
Thank you. Let me quickly start this one on the red screen as well.
So you see some.
There we go. I hope that's all visible for you.
Yep.
There we go. All right, so welcome everyone. Thank you all for being here and giving me the opportunity to give a little talk about my research. So the title of the talk is Observing Transients in a Simulated Universe. And there might be a few things that you know in that and a few things that might be a little bit unknown yet. So first, a little bit about me, which is probably unknown. I'm Max. I'm a PhD student at the University of Auckland, and I am originally from the Netherlands. I did my undergrad there and my master's, both in astrophysics, specifically mergers, and after some neutrino physics, so more particle physics. And in my spare time, I do running, swimming, and tramping. Actually, bike too, but I don't do triathlons. That's a little bit too much. So with me at the University of Auckland, I work with a big group of people. Some of them there, some of them in the UK. There's Jan Eldridge, who you might know, Eloise. There's me, of course. There's Petra, who will be talking after me. Wouter and so on has just started their PhDs. Sean is doing masters, and Gleb and Adib, who are doing their honors project with Jan. And then there's Elizabeth, Lynn, and John, with Elizabeth in the UK and Lynn and John originally working here with Jan and contributing to this research as well. So as the title suggests, we're going to be observing transients. So what are transients? Transients are short-lived astrophysical events, and you might know a few. Like eclipses are transients. We have gravitational microlensing, supernovae, gravitational wave events, gamma-ray bursts, novae, transits. These are all in the classification of transients because they're short-lived astrophysical events compared to someone like a star that lives billions of years. These only take hours, sometimes days, seconds even. But the two I am specifically looking at are gravitational wave events and supernovae, which both relate to the evolution of stars. So these transients, specifically the supernova and gravitational waves, can tell us something about the stellar population, where they come from. This tells us basically how the stellar population kind of determines what kind of stellar evolution has happened and what kind of environment these stars were born in. So we kind of want to use the transients to figure out what the stellar population was made of. But this relation of how this relates back to the stellar population is not always clear. So we use models to figure out, go from the stellar population back to the transients. For the transients, I think we should get into a little bit more detail, because for the supernovae, there are two main observable types. There is a type 1 and the type 2. And they're basically this distinction is only made based on the available resource or the available light we see. So for type 1, we don't see hydrogen in their spectrum, while in type 2, we do see hydrogen. These can be split up in subtypes. We have type 1a, type 1b, type 1c, and type 2. In this case, these are basically all coming from a different sort of progenitor. That means the star that was originally there and that one exploded in the supernovae. And so there is the type 1a, 1c, and type 2 that originally come from a core collapse supernovae. Well, these events, or these core collapse supernovae, is basically a star that's imploding, the core imploding and then exploding. And it basically follows the current star formation, that is the amount of stars being formed, relatively closely due to the short lifetime of these stars. And then there's a type 1a, which is a thermonuclear explosion, which basically happens if you get two white dwarfs or a single white dwarf gaining material and that exploding. Because this is a binary interaction, you have a evolutionary process that is a lot longer than for the core collapse. And so, therefore, this tracks the older star formation. So that's kind of looking back further in the past. Then on the gravitational wave sides, we have, these are basically originating from compact objects. These are black holes or neutron stars. And they're very heavy. And basically, because they're so heavy, and some probably know here, is they distort the space-time around them. And so in a binary, this will sort of create a rippling effect going through space-time that since 2016 we can actually measure. And Petra will be talking more about measuring these. But eventually they merge, and then that signal we measure. And so there's also the combination of a neutron star and a black hole that can merge. I won't go into that now, but that is something that can be interesting as well. Now, for these events, there's also quite the relation back to the stellar evolution. And what does it say about, indeed, the stellar population, about the stellar evolution or the environment? And so the neutron stars, tell us specifically, are really sensitive to stellar evolution, to binary evolution specifically. That is, for example, if you have two stars and one explodes, this explosion can cause the other star to become unbound and just start traveling, or adjust the orbit in some way. And so the binary evolution in that sense is important. For the black holes, it's the metallicity of their environment that is important. While at the same time also the amount of matter available to create stars is very important. And so you have this sort of balance where the neutron stars really look at the binary evolution, while the black holes really look at the environment itself. So the talk, of course, was called Observing Transients in a Simulated Universe. So with this information about the different events, we now want to predict them. And in this case, I have taken 4 different ones as an example here. The type 1a circular club supernovae, the double neutron stars, and the double black hole ones. And so for this, we need several things. And I've already kind of mentioned a few of them, 2 of them. And those are the stellar population component, which for we use a population synthesis. I will get into that in a little bit further. And the star formation rate, which in this case comes from cosmological simulations. So to understand the star formation rate, we'll have to go into a little bit of depth because this has 2 components. There is a metallicity evolution, that is the amount of elements except hydrogen and helium. Of course, astronomers and astrophysicists are kind of like everything else is a metal. And the cosmic star formation history. And the cosmic star formation history is all the material available or that formed stars. And so this is over the whole history of the universe. And to be able to do that, we have to look at something called redshift. And redshift is basically an observation of how far something is or how old something is. And so we can see basically it's the following of this is where it comes from is if an object moves away from us, we get a Doppler shift. It turns red. This is like hearing an ambulance move away from you and hearing the sound change or coming towards you. That together with the fact that the universe is expanding, and so therefore distances become larger over time, we basically get more redshift over time. Because it's getting bigger. And so we can create this, that's not really that well visible, but we can create basically a map of redshift of the distance from basically away from us. And so also a certain measurement of how old it is, because the later it is in time, the more expansion is taking place, and therefore the redder it is. So with this redshift in mind, we now go take a look at the larger picture, which is the star formation rate. Originally, or very commonly, this is taken from some sort of observations and then measured through UV and infrared. Another approach to this is to take cosmological simulations, which take the very large scale of the universe and then bring it all the way down to go all the way down to the size of a galaxy itself. So you can see here, for example, this is the Eagle simulation, and this goes all the way from large-scale structures in that simulation in the universe till smaller and smaller, all the way up to a galaxy. And so per galaxy, we can basically extract this information about how much stars are being formed throughout redshift, throughout cosmic time. And so this plot might be a little bit complex, but basically what we get is we get an amount of material being formed over the age, over how old something gets. And basically this shape is important because it determines how much stars are being formed. And with that, also the metallicity, so how much everything except hydrogen and helium is being formed. And so the redder here, the more metals are being formed. And so the closer we are to the red, the higher the metallicity is, so the more other metals, the more metals there are in the universe. And this is expected where we have more metals on the left. This is, however, from sort of an approximation. So if you then look at these simulations, there are two things I want you to take away from here. The first thing is that the simulations, the three on the right, start much later in their star formation. You see that they only start here, while here there's already quite a lot of evolution. And so star formation starts later. That's the first one I want you to take away from this. The second one is we have higher metallicity at earlier ages. So for example, the dark red only starts about here, while for the simulations, it's already around 6 or 8. This will impact the evolution and the type of events we'll see in our predictions. And so this is the first component. We have now basically looked at the star formation, and those come from the different cosmological simulations. Then we have our second component, the stellar evolution that we need to address. And so you use a population synthesis code for that. In this case, we use BPAS, which is created by my supervisor and Elizabeth. That basically works as follows. We create a bunch of stars all at the same time during a starburst moment. And then we evolve them according to an evolutionary code and record what happens to these events. So we might have some binary stars, and some might merge or some might separate over time. And for the single stars, for example, we might have a star that explodes in a 1B explosion, or we get two stars that sort of rotate, and instead of merging, one explodes and then the other one merges. And so we get all these different events that are possible. And so we record them and look and see what happens. And so we call this the delay time distribution. That is from the time when something was born till it exploded or something interesting happened to it. And so with this, we can then apply it to our, combine it with our stellar formation rate. However, it's important to note for this one, for the delay time distribution, is that if we have different metals in our initial population of stars that we created, if the metals are different, basically our distribution will be different. And so it's really important to note that this is metallicity dependent, and that is, if we have more metals, we might get different distributions. So now we have the two components, the stellar evolution and the star formation rate. And now we can take them together and predict the amount of events we get. And so I will only mostly go into 1A and compare them against observations, and then give the results for the others. So for the 1A, we get a prediction, which are the 4 colored lines, of which the red one is the empirical, from observations, and the rest is from the simulations. And so from theory, we know that these events, the type 1As, follow the older star formation closely. And now we can actually start to observe them against the rate that was being observed, the total rate. And so these are all measurements, and you can see there are quite large errors on them. And that is because there are quite a lot of additional things to take into consideration, such as the measurement of where they are. And basically, within the observation, we can say, oh, they're all kind of within the constraints of, of our observations. And so that's also a kind of our conclusion in this case. It can be according to this distribution or in these observations be any of these. And even they have all kind of similar distributions as well. They're similar shape. But that's why we have these multiple events, because we can all create them from a single population. And so the 1A's just gives us that it can be any model. But if we then look at the core collapse supernovae, which were the ones that imploded and had a relatively short lifetime, we basically get a sort of separation in observations and in the models. So we have these distributions here and the ones at the top. And so there is already quite a disconnect here in the observations, but also in the models that follow it. Because you can see that the green and the orange line follow the bottom observations, while the red one follows the top one. And so this gives us already an insight that something might be going on. And so this follows the current star formation more closely. And so we then can look at something like the black hole ones, which completely disagree. Because these are the observations down here, and these are the actual predictions. And so even though this might not be correct, it does give us some information. It can tell us basically, oh, we might be having too much low metallicity star formation, which is what the black holes depend on, or our binary evolution might be wrong. But if you remember, the neutron-neutron star was mostly dependent on the binary parameters. So by having a look at them, we can get an idea if actually the second question is wrong, if our binary parameters are wrong. And so for this one, we see that it actually really lines up with the predictions and the sim observations. And so from this, we can basically also say, oh, maybe our parameters are correct. And so basically from this, we don't really know yet what is going on and where it lies. And that is, in a way, there's a lot of information in pack in here, and it needs more time, and we can expand upon it. We can use other events that are around to also constrain this even further. So for example, we have only looked at this now. One thing we can do is look at the different subtypes in the core collapse supernovae, because they also have slightly different mass progenitors. Another one we can look at is apparent stability supernovae. That comes from a very heavy star that has sort of imploded in a way, or has been disrupted because electrons and positrons have been created. But that one hasn't been observed yet. That's one possibility. The other one is long gamma ray bursts, which is an observational idea which has been observed, but the progenitor is not always as clear. And so these two are really metallicity dependent. And so this can give us another insight if our black hole evolution, which was very metallicity dependent as well, is correct or not, or if it's something in the binary, if it's something in the stellar evolution, or if it's something in the environment. Together with that, a relation between the long gamma ray burst or the type 1c might be able to improve us in seeing what exactly is going on here, and if it's the environment or if it's just our idea of what's going on in the evolution. And with that, I want to thank you. And if there are any questions, please let me know.
In the star formation rate graph, what was the black line at the top?
So the black line on top is the total.
Right.
So let me go back real quick. So yeah, for example, for each one of these, it's a total amount of stellar material being formed. And I think sort of separate it into each metallicity, specifically a certain amount of bins to make it, to be able to perform our evolution with those stellar models. So we form a delay time distribution for a certain amount of metallicities, and then combine that with those different lines, with these different lines, basically, to create our prediction of how many events we expect. Mm-hmm.
Yeah, could you comment on how you decide on what the initial seed population of stars is?
So the population of, in what sense? Of like our stellar population?
Yeah. It's like a mix, like a Bristol muscle diagram.
So for this, the starburst, right? So this is created through sort of the initial mass function, and that is basically something that comes from observations. So therefore, in that we decide how many stars of what kind of mass we get, and also you get somewhat from observations and predictions, you get your amount of binaries and your parameters in these binaries. So these come from very often from observations or simulations that then have predicted sort of our have predicted the observation or have predicted something that aligns with the observations. Mm-hmm. I saw another question around there as well.
Back to that graph which had all the evolutions.
Yeah.
The empirical one starts with the population, which presumably is the Big Bang, but is that what the others don't because they wait until stuff?
So why this one starts far earlier in the star formation? Is that your question? So part of it is, as far as I'm aware, is that I think it should be said like Redshift 14 is really early at the beginning of the universe.
Oh, okay. It's Redshift for
Yeah, and so it matters, but how much it's icky. But it is such a big difference, and you can see it as well that here you have very little low metallicity star formation until you get into the high metallicity. And so part of it is how these models generate or start star formation. One of them is you need you have an amount of gas, and that's what they start with, and then that slowly starts to sort of collapse on itself based on the dark matter in there, because it's a combination of dark matter and baryonic matter. And so it starts to collapse on itself, and then at a certain point, a density threshold is reached. And then they say, we now start to create stuff in our simulation. And so that's where that star formation rate comes from. And I think at that point, it's at 14 where they are like, it starts now, if that makes sense. Then the threshold is reached. Mm-hmm. Oh,
There's going to be my
it's a
next question
follow-up
about the role of dark matter that's taken into account.
Yes, so it's a very good question, actually. These two simulations, the Illustrious and the Eagle simulation, both combine dark matter and baryonic matter in the same model. And so it's both taken into account at the same time. The Millennium simulation this one is relatively old, and relatively, it's 2005. Well, luckily I was already around, but yeah. I mean, the Illustrious and Eagle one are 2018, and the Millennium is only dark matter, but does galaxy evolution on top of that. So they have first gone a full run of the dark matter and see how that collapsed. And then they were like, all right, at certain points we think here, according to some rules, here galaxies form. And so with that formation is basically on top of that after they had completed the run. While for the Illustrious and TNG, it's done at the same time. And a question here?
Expecting merging galaxies have any effect here?
Oh, yes, yes. So all these galaxies interact, or not all of them, but like they can interact. And so you get very jumpy star formation as well, based on if there's a merger, very often you get suddenly a burst of star formation, because you get like a lot of gas coming together and that just starts to collapse as well. Mm-hmm. Any other questions? Yeah, go ahead. No worries.
To be clear, the empirical one, that's actual observations.
So yes, it comes from observations. However, the metallicity evolution does not. So it comes from, that is a sort of parameterization of what we think would happen. The fit itself of the total of the black line, that is done using UV and infrared observations. But there's a lot of error in there. Wait, I can actually, if you have a second, I think I have a hidden slide for that one. Where am I? Yeah, there we go. So this, for example, is the observations. And we have infrared and UV, and this is basically combined what the fit is on. And so this goes up to Redshift 8, so it's not really that far. And you can see it is relatively constrained, but there is also quite a lot of change in there. And so it's a fit, and you don't really know how this necessarily is true, or like, yeah. And there is uncertainty in there, basically. But it comes from observations, yes.
How much computing power does running these simulations take?
So the major simulations use, like the cosmological ones take a lot of computing power. The exact number, I'm not sure, because they are run once, mostly. And then the data is made publicly available. And so I know from the Millennium simulation, TNG, that each of them took, at least the TNG one took more than a month to run on like a supercluster. So it's a lot of computing power, yeah. They have the power, they have they have it available. And it's very interesting because you can get such small detail as well. All right, any more questions? Otherwise, I would like to give it over to Petra.
Thank you. Cool.
But yeah, it's that one, I think.
All right, good evening, everyone. Welcome to the evening sessions. It's just before bedtime. Hopefully, I will keep you awake. And thank you very much, Max. Theory is important, but I don't do a lot of theories now. I do a bit of real data analysis, well, real synthetic data. So my topic for my PhD study is a mouthful. I'm not going to go through the topic. We'll just move on, shall we? I'll explain each word in a moment. So I'm a first-year PhD student, hopefully finishing my first year soon, and I've got 2 supervisors. Awesome, so you've got 2 people and can help me out to go through the 3 years. And outline, we'll just skip that. We'll go through the first thing. Gravitational waves. So that's the big thing. If you want to get a job in the field, it's probably you want to do this now. I think nuclear physics and atomic physics, I think they're all, yeah, let's not talk about those. So why gravitational waves? So I'm going to introduce that. It produces a solution for Einstein's equation. So, well, that's important because that solution tells us something that exists, but we may not be detect. And if we can detect it, we can get a Nobel Prize. So the second thing, it travels at the speed of light. But it's not light. It's not light, but it travels at the speed of light. Isn't that weird? I think that's really awesome. So let's move on to the next property. If you can, let's say, feel the gravitational wave, you can feel it's massaging you horizontally or vertically. So there's 2 polarization. They're in about 45-degree kind of angle of each other. And it only reacts with matter very weakly. So it's going through you now, so you don't feel it. That is why it's very, very hard to detect them. They're so weak. And what about the sources? Let's look at the sources of gravitational waves. So the first one is compact binaries in spiral. So on the right-hand side corner, Max already talked about, you got compact object. There are 3 types of compact object. Little ones, white dwarf, very compact, neutron stars, black holes, and they can go around each other and lose energy while they merge into something else. That's one. The second one is a supernova or gamma ray burst that gives you a signal that's a sudden signal. So it looks like that. Probably doesn't look like that, but you can imagine that. The third one I found is very interesting. It's the pulsar in our galaxy or in maybe other galaxies. It's giving you a periodic signal. So this is it's not really playing. So basically it's like a neutron star, but it's pulsating. So it's a pulsar we can measure the signal, we can detect the signal with pulsar timing array. But this is what, not what I do. I do something else. I collect all of them. So I collect all the information, all the signals from space, and hoping at some stage I can capture that gravitational wave and tell you a story about the source of it. So this is, we call it a stochastic background, or stochastic gravitational wave background. What it really means, stochastic, it just means diffused, means everything. Everything from early universe until maybe recent, the history of the universe. Anything that can produce the gravitational wave, we count all of them together, stochastic. So what? Well, Einstein predicted, and he said, it's very hard to measure. Don't be bothered. Don't even bother. So this number tells you it's very small. If you do a bit of math, you know there's 27 zeros before decimal point. So that's how small it is. And we can't measure it. The first indirect measurement, it was in 1973 or 74 or something. It was indirect because we actually didn't measure the wave, but we did measure the decrease of the orbit of two pulsating neutron stars. And that got a Nobel Prize, yes. And that fits the prediction of general relativity. So you put everything in, put on a computer, drawing the dots, just like when you in your sanctuary school physics class, and you found it fits. If it fits, it must be right. So usually that's the case. So if it's real, how do we measure it? So it's been 20 years, but only recently, in 2015, we have the first direct observation from LIGO and Virgo collaborate. They measured the first direct two black holes merging into each other. So apart from Virgo and LIGO, we have all the other countries joined the big collaboration, and that's really awesome. Imagine Alpha Centauri, we'll do that. We can look at that later. And Proxima Centauri as well. You can't really see it, but we know it's there. It's not a double star. Unfortunately, it's a triple. And the sensitivity of this instrument, the L-shaped 4-kilometer arm, can measure the width of your hair at a distance of Alpha Centauri. Imagine the sensitivity. So that's going to be awesome. It's going to make a lot of money. Hopefully, we can detect that gravitational wave. And this is 2016, only 4 years ago. I was still teaching in the high school. And they had 3 observations of 2 black holes merging into one. And you can see, let's do a bit of math. What's 35 plus, let's say, 28? 63. What about the total? Not quite 63. I think it's maybe a few solar mass less. But the idea is, when you merge, you lose a bit of energy. The final mass is not the sum of the 2 initial mass. What happened? It means that Einstein's probably right. The energy has been radiated out while they merge in the form of gravitational wave. A few years later, it was sometime, 2 months ago maybe, the first half of the 3rd run of LIGO Virgo Collaborate, they announced extra numbers. Now, there are total 50 different observations. Imagine if they announced this, the second half of the 3rd round, they probably will confirm more candidates. And we have all these things we can work with now, not just 3. So for me, actually, it's good news when I started now. If I started 4 years ago, I would still be doing it because I only had 3 data points to work with. Now I have 50. That's good. So that quadruples my graduation rate. Let's move on. If we can do something really well on Earth, and we can do it better in space. Because we believe that atmosphere is always stopping us to learn things better. But in this case, it's kind of complementary. In space, we can launch something else. ESA, European Space Agency, decided we're going to do something better. So in a few years, they will be launching 3 spacecraft connected by nothing but gravity between them. And they will be having laser beams, just like LIGO instrument, bouncing each other and measuring the the patterns or distraction constructions of the lasers between them, the mirrors, all that thing, engineering stuff. So they would be, so Earth is somewhere here. So it forms a regular polygon, an equilateral triangle, orbits around the sun about 4 times, so 4 years observation time. During that 4 years, minus all the times that it's going to change its direction, about 3 year worth of data that's worthwhile to look at. So what if we have this instrument? It's called Laser Interferometer Space Antenna. It measures the different spectrum. Imagine the spectrum of light, radiation. We all know that now. We've known it for probably 100 years. And this is a different type of spectrum based on frequency. This is LIGO spectrum. They measure up to maybe kilohertz, that kind of wave, gravitational wave. And LISA measures millihertz, so slightly smaller. So that means we're expanding our search window. We're looking for something, massive black holes that LISA can't find, but we can. Or extreme mass ratio inspired, some really small, some really big, and they kind of become one, something like that. And what about this black line here? This is called the sensitivity curve, or let's imagine anything above it. Yes, you can observe. Anything below that, you can't observe it. So we're looking for anything here. And this one up there, that's a little bit sad, but actually you can still observe. That's called International Pulsar Timing Array. That takes even longer. That can measure very, very tiny frequencies. But what we can, I feel really happy when I look at it. I see the area of this is really big. Means that the chance of us using LISA to observe or capture the gravitational waves is very high because we believe that it covers that much area. This is I think this is a real science picture, isn't it? It's real science. Good. Yeah, I got it from the legit website. Yeah, I didn't produce it. It's very hard to produce these graphs. All right. Okay, so that's all background. This is my job now. When I receive the signal, for example, this is about about 115 days of signals. So here, just time in seconds. You can't really see. So it's 1 with 7 zeros. That's seconds. And vertically, that measures the amplitude of the signal that's being converted. So thinking about the laser construction patterns, and you form those different, form those amplitudes. So you can't really see anything. This contains stochastic gravitational wave background. Means that all the information we want to know. We want binary stars. We want massive black holes. We want to know white dwarfs, white dwarf binaries, and noise. So everything's in here. It's called time dependent because it depends on which time you look at. It looks slightly different and depends on time. That's very nasty. If anyone's got a little bit of engineering background or maybe sound processing background, you know the first thing you do is for a transformer. What does it mean? I don't know. You chuck into your computer program nowadays. You can use Python, you can use R, you can use Fortran, all that, learn a few code. The thing is, I found science. You learn the science, you learn, I'm off topic now. Okay, right, you're still looking at the same signal, but now the amplitude is still the same thing, but the x-axis, the horizontal axis changed. It's no longer time, it's frequency. So we are looking at millihertz. Look, from 0 to 0.1, it's roughly millihertz. So this signal is slightly better looking. So we know maybe something's going on, maybe not. We're not sure. This signal is from LISA training or LISA data challenge. So a few years back, they made some data. They put some signal in it. They put some noise in it, and they put it online. Okay, you go. Students, price, $500. Of course, I didn't get it because I'm always very slow. But I like it. It's really cool. You can learn from it. So what can we do? What can I do about it? I can't just look at each dot and imagine and then maybe replot it. It's not the way. So I use something that I never thought about using it. I use statistics. So I use Bayesian parameter estimation. I'll explain that. So this is the result you want to get. So your prediction. So posterior, we call it. Forget about the bottom bit. The top first, the P. This is likelihood, some kind of probability distribution. Here is your prior, means that things that you already know, your prior knowledge. And without the bottom means this times that gives you that. A times B gives you C, basically. And you check into a computer program, and you can figure out a result. So what do I need to do before I use this method? This getting into the things, I have to really think about it. Now we're getting into stats, but computer programming. No, it's astrophysics. No, it's maths. It's everything. So I need 4 things at the moment. For the noise, imagine the signal has 2 parts. I've got my gravitational wave, this fancy signal, and I have the noise. For the noise, I have a P and A. Doesn't matter whatever they are. There are 2 variables, changing terms, that determines what this noise maybe look like. And for the signal that I want to know the information about the binary stars, I have slope and amplitude. Doesn't matter what they are 2 changing variables that determines what the signal may look like. And I check them into an equation or a program. You have to do a bit of coding. Python for the younger ones, you can get into Python. But before I do that, I'm going to do a bit of an assumption. The simpler, the better, and we can add more stuff to it. We're going to assume the thing is isotropic, means every direction you look at is the same. Gaussian, doesn't matter. It means that the average value is 0. We're going to assume its average value is 0, and it's oscillating between zeros. So there's a result. I only have 1 graph. You won. So what this graph really tells me, this is frequency. You may say, hey, Petra, you said there's 0.1 here. No, this is angular frequency. You have to divide it by 2 pi. Never mind, this is what the software does. So that's angular frequency. Here's a non-normalized, something called a PSD. It means power, how much power the signal gives out. Forget about the log. It just means a different scale. It means how much power. This gray color is a small chunk of that previous data I showed you. I put it into a power. It means that at this frequency, angular frequency, there's a slightly more power there. At this angular frequency, the power is slightly less. So this gray colored is the real data. Well, they produce their mock data. I call it real data. So what I've done is I'm using Bayesian stats, and I've found parameters, boom, into a black box and push out the black line in the middle. That's the average, my prediction. My interpolation means that I'm finding best fit to fit the real data, and the blue ones, it's my error, 90%. Not like Max ones is all the way, a couple of graphs all the way across the graph. Yeah, but this one's not too bad. I think it's pretty cool. And the method is quite complicated. And myself, I think I still need to understand it. It's not just simply plotting it. We're cutting this frequency into smaller chunks to process. All right, so bit of a discussion. So usually when we look at waveform or signals, gravitational wave, there's a simple assumption that maybe is power law shape. What does it mean is there's a predictable shape, but actually for a stochastic wave background, we can't do that. So my initial assumption, I had to assume the power law shape. So my next step is not to assume it, because it doesn't work for the background. The second one is there are also other unknown noises. What I have assumed is the P and A variables, but in fact, they are way more. It's not just the instrument. There's 3 spacecrafts orbiting around the Earth. Apart from that, it could be something else. It could be alien invasion. Who knows? So there has to be something else we need to consider that I need to consult with Max's team to ask him to tell me more about the binary stars. How do they evolve? Is there anything else that we don't know? Can I add another variable to make my prediction or analysis better? The third one is I assumed 4 parameters, P, A, amplitude, and slope. But the real life is complicated. There are more, maybe infinite number of parameters. So I have to use something else called non-parametric rather than parametric Bayesian to analyze the data, to profile the suspect. Because we are actually just looking at the fingerprints and trying to find which one fit. But a lot of times it's actually fingerprints on fingerprints. It's very hard to find the suspect. And I'm looking forward to discover the beauty of finding the suspect. Thank you very much. Any questions? Yes?
During that power distribution there, your credible region is quite close to your median, but the data is quite spread.
Yes.
Is that a measure of the quality of the data, or the noise of the data, or the?
No, because this gray region has the 90% is with respect to the median, not with respect to the actual data. That's why it doesn't include 90% of the data, but only the 90% of the prediction.
So if it was a 99% 3?
Yeah, it'll be just slightly wider. It still won't include all this, because what the computer program would do is they smooth the data. So instead, what they do is they will, in a simpler term, is they will pick the average of, for example, here and here, and then they're going to assume the real data is somewhere here. So the smoothing is hidden in the programming, because a lot of times without doing smoothing, you're including a lot of residue or noise. And doing smoothing, potentially you can get rid of the noise. Yeah, so it's now it's part of the package, I think.
And this was on your simulated data?
Yeah.
Have you applied it to some of the actual observations?
There is no actual data.
Oh, there's no.
No. Because LISA, so the instrument of this guy, won't be launched until 2025, I believe. Yeah, it was delayed. I think it was supposed to be launched in 2 years, but I think it's delayed again. But they launched a smaller version. They call it Pathfinder. Thank you. They launched a small version. And the small version, unfortunately, because it's so small, and the arm distance is not 5 million kilometers anymore, it's very small, so they can only measure a certain frequency. And that frequency allows us to understand the white noise really well. And then it works really well for measuring the white noise, but not the actual signal. Yeah. So we don't actually have that instrument.
My question was going to be, what's determining the time scale? I mean, 2034, some of us are going to be dead then, and this is going to produce some really interesting information about the early universe, etc.
I think apart from funding is probably funding. Yeah. I'm not sure. Maybe politics, because this.
There were some developmental issues. So,
Technology wasn't quite ready.
Yeah.
Well, but
Yeah.
40 years.
Yeah, it is. For this one, I'm also part of the consortium meetings. I listen to a lot of the discussions about very technical stuff, HR, who to hire, who to fire, that kind of thing. So maybe that's where the money is going. Yeah, the good question. It's something I'd like to ask. Yeah. Another question. Yeah.
Petra, when you were teaching
Yeah.
mathematics, how many students' brains did you explode?
Well, my technique is entertain them first. When they like you, they're more likely to listen to you. Yeah. So I don't know. Hopefully quite a few. Yes.
If you go back to the population of LIGO objects,
How far away are most of those that have been detected?
What's the furthest? 2 point something billion?
5,000 gigaparsecs.
5 times 3, times 4. Almost 2 billion? 15 billion. Light years.
That's quite
Furthest.
Because I was thinking of Max's presentation, there wasn't much in the higher redshifts at all that's been detected, but perhaps with the new upgrade, it will
That's
push
right.
that further.
Yeah.
For him, for his research.
That's right. The hope for us is to really to learn the beginning of the universe, because that's something that we haven't seen through light, but we can see through gravitational wave spectrums. That's what we hope. And to create a new branch of science. It's already started. And there's probably one job every week coming out, different type of jobs. Yeah. Any other questions?
Anything online at all? Okay. Well, thanks very much, Petra and Matt.
Right. Thank you very much.
Just before we finish, there is a summary slide afterwards. I just like with a small gift. The RASNZ calendar for 2021.
Thank you very much.